Hello everybody. Today we are going to talk about fringe width beta. In the last class we have studied Young's double slit experiment. In that experiment we got the expression for linear distances linear distances of bright and dark from the center of the final screen. So it was something like this. This was the final screen. Here's the O, and let it be any nth bright fringe. The distance from O to the bright fringe was x sub n, and that x sub n was n lambda L by d. Okay, where d is the distance between sources, and lambda is the wavelength of light which we are using, the monochromatic light source, and L is the distance from slits to the final screen. So with this expression, with this equation, we can find out the distance of any bright fringe from O. If you want to get the second bright distance from O, put n equal to 2, you'll get it. 3, 4, 5, likewise any distance any bright you can find out. Now our aim is to find out the fringe width beta. Fringe width, we denote it with beta. Now what is fringe width? Fringe width is the successive distance between any two bright or any two dark, because in this interference pattern we have the same the same width for bright and dark. So that's why you can take the any successive distance between two bright or any successive distance between any dark. So here I am finding the beta by using the successive distances between two bright fringes. Okay, here you will be having let it be the first bright, and suppose at some here at some at this position I am getting the second bright fringe. Okay, so if we subtract the distance between these two things, if we do x2 minus x1, that will give me the fringe width beta. Okay, that will give me fringe width beta, and that is what we are going to find out now. So first I'll find out the distance of first bright from O, that is x1. It will be n will be equal to 1 lambda L by d. Let this be my equation 1. And now I have to find out x2. What I have to do? I just have to replace this n with 2. It will be n x sub 2 lambda L by d. Let this be equation 2. If I do 2 minus 1, I'll be getting x2 minus x1, and that is my fringe width beta, and that is equals to 2 lambda L by d minus lambda L by d. And now from here I can get lambda L by d is my fringe width beta. So how I can get the fringe width beta? If you know the lambda, the light which we are using, and L is the distance between the slits and the final screen, and D is the distance between the slits. This is how you can find out the fringe width beta. And once if you know the fringe width beta, and with this expression we can also find out one thing, that is wavelength lambda. So the lambda can be written as beta d by L. So the wavelength, if you don't know which wavelength of light you are using, you can use the Young's double slit experiment, and with that experiment you can find out the wavelength of light which you are using and which is unknown to you. Hello everybody, today we are going to talk about coherent source. It's the most important thing to have the interference pattern. There are some conditions. If you fulfill the conditions, then only you can have the interference pattern on the final screen. It is not like just any two sources, take the any two sources and you can have the interference pattern on the final screen. It is not that easy. To have an interference pattern, we should have coherent sources. And today I am going to talk about what are those coherent sources and what I mean by coherent sources and why they are that much important in producing the coherent, not in producing the interference pattern. So let's get started. First, I'll tell you what are coherent sources. You see, for like it is not just for applicable for the light waves. You can have the coherent water waves. You can have the coherent sound waves. And the phenomena of interference is just it is not just limited to the light waves. You can have the phenomena of interference with sound wave also, and you can have the phenomena of interference with water wave also, as I discussed in my earlier class. If you have anything that which is having the wave nature can undergo interference. I'll give you few examples, and with those things you'll get the idea and you'll get the feeling for the coherent sources. Suppose I have two sources, okay, and these two sources I'll be using for getting the interference pattern on the final screen. Suppose this is my final screen where I want to get the interference pattern due to these two sources. The first wave from this source, okay, when I can say them as coherent is that if you have the other source having the same wavelength as that of the first source, then only you can call them as coherent source. You see, from here to here it is having lambda, and this ray is also having lambda from there to there. Same wavelength, and the other thing is that in a second, if this wave is going up and down two times, this wave should also undergo two oscillation, two times up and down in a second. So the condition, then only you can say them as coherent. What are those? You should have the same wavelength. The other thing is that you should have the same frequency. Indirectly, when you have the same wavelength, they will be having same frequency. So now I will tell you why you must have coherent source to have the interference pattern. Now I am trying to relate the final interference pattern with this thing. If suppose instead of having a coherent source, if you just pick any two light sources and which don't have the common wavelength among them and which don't have the same frequency, so I'll try to show you why you can't get the interference pattern with those sources. Suppose instead of having this source, I am having a source whose wavelength is bit different as compared to the first source. Now I am trying to get the interference pattern due to these two sources, S1 and S2. Now I'll tell you why I will not get the interference due to these waves. You see, whenever you are getting a dark spot on the final screen, it means what? The first source is giving you the top and the second source is giving you its bottom. Then only you can have the destructive interference. But you see, in here when these two light rays will meet at some point, because if you have the same wavelength, they'll be having same amplitude 1 meter. Suppose for example, more possible, I'll take it as 1 nanometer, and this is also having 1 nanometer. Okay, and here I have a wave, a different thing, and here it is having let it be 0.5 nanometer amplitude. So its bottom is having same 0.5 nanometer amplitude. When they both meet destructively, it will be having 1 nanometer, and this one will be having 0.5 nanometer on the final screen. I'm talking about S1 and S2. When they both will meet on the final screen, you can't have a point on the final screen where the intensity, where the light is completely vanishing. Why? Because it is half, it is the one, and here you have the half. So if they cancel each other, we have studied the principle of superposition. From that, we'll add, okay, we'll add the vectors, like here you have 1 and here you have 0.5. So it won't cancel out. At the end of the day, we'll be having a wave which can have the 0.5 amplitude, 0.5 nanometer amplitudes. So that's why the coherent source is important to have the interference pattern. If you don't have it, something like this will happen. You see, the source number S1 and S2 are not coherent. That's why you will not get a interference pattern on the final screen. And S1 and S2, let it be S3, they are coherent. Now if it will be 1 nanometer and this is 1 nanometer, upside this wave is having the momentum upward, and 1 nanometer, this one is having downward 1 nanometer, so they will cancel their momentas, okay, when they meet at some point. Okay, so that's how you can have a complete dark in here. Likewise, same thing applies for the bright. Same thing, same condition applies for the bright region. Okay, so that's why the coherent sources are important to have the interference pattern. Now, this is not just there are a few more properties of a coherent source. A few more things are there, and if you have those things also, then also you can say them as coherent. And what are those things? We'll check it out now. Suppose I'll always compare my other wave with my first source. Okay, now I'm gonna take another source. This source now, what I'm telling you is that the source S3, I've already taken that, so it will be S4. The source S1 and S4 both are coherent. You see, I've changed. Here, this one was starting from its top, but this S4 is starting from its bottom and S1 is starting from its top. So I'm calling them as S1, and the S2 are also called as, they can also be coherent. How come? You see, first thing is that they both have the same wavelength. Here's you have the bottom of this, and here's also you have the bottom of this. If you compare, they both have the same wavelength. One condition got satisfied. The other thing is that same frequency. It means if this is oscillating 2 times in a second, this will also oscillate 2 times in a second. But the only thing is that between the S1 and S2, there is a phase difference of pi, 180 degrees. This wave is looking upward, and this wave is exactly looking downward. What is the phase difference between these two waves? This wave is downward and the other phase is kind of upward. So the phase difference is pi 180 degree. So that's how that doesn't make any difference. Like they are still coherent sources. No big deal. Okay. Now one more example I'll take. S5. These two sources S1 and S4 will also produce the interference pattern on the final screen, but it will be bit different from the coherent sources S1 and S3. S1 and S3, if you use coherent sources S1 and S3 at the center on the final screen, it is sure that you are gonna get a bright spot. Why? Because when they meet, likewise top, when they meet on the final screen, so S1 and S3. Okay, due to S1 and S3, if I see the interference pattern on the final screen, at the center I'll be getting a bright spot. Why? Because they are in phase. They are in phase means exactly the same distance they'll travel to reach the point O on the final screen. Same distance means if this ray is on its top, the other one, S3, will also be on its top. So that's why you are going to get a bright spot at the center. But if you take a coherent sources who is they are having a phase difference of pi 180 degrees. So they both have the phase difference of pi. These two sources having the phase difference of pi. In this case, in this coherent sources, you won't get a bright spot at the center. Why? Because after traveling the equal path from their sources to the point O, they will be meeting. The phase difference between them will be 180 degree, because at the start they were having the phase difference 180 degree, and at the end where they are meeting at point O, there also they can have the phase difference 180 only. Why? Because they are traveling exactly same distance. When this got hit, if I take this situation, this will be on its moving upward and this ray is moving downward. So when they meet on the final screen O, they'll be giving you destructive interference at the center on the final screen. That is what the difference is. But you will get the interference pattern. Okay. Now I'll show you one more example, and this is going to be incoherent sources. Like if you have a source from where you are getting a wave, but whose wavelength is not same and whose wavelength is changing with time. Here's you have a bigger wavelength and here's you have a less wavelength. So if I compare source number 1 with the source number 5th one, they are not coherent. Because what is the condition for the coherent? They should have the same wavelength. You see, this thing is not having same wavelength as this one, and the other thing is that its wavelength is keep on changing with time. So that is not allowed. So they are not coherent. If you take these two rays and try to have the interference pattern on the final screen, the same thing will happen, which happened with S1 and S2. As I told you, you won't get any place on the final screen where you can have a destructive interference. It like the whole screen will be having light on it. There will be no any spot where you can have a destructive interference, because they won't cancel each other perfectly. Here's you are getting interference pattern. Okay, it's a symmetrical thing. Okay, to have a symmetrical interference, that interference pattern is a symmetry. Okay, so if you want to see that much symmetrical beautiful phenomena of light, you should use waves which sources which have some symmetry between them. If you don't have the symmetry between your sources, how would you expect to get the symmetry from the interference pattern? Won't be having any symmetry. There will be interference, but that won't be sharp. Okay, now in the source S1 and S5, the other condition is that if you are getting a constant phase difference between the sources, like here as you see between S1 and S4, you are getting phase difference pi, again pi, again pi. This is at its bottom, this is at its top. Again same phase difference. Either you can have a same phase or you can have the constant phase difference between the sources. Then only you can call them as coherent. You take the example of the first and fifth source. If I take any instant, you see here's it is having zero phase difference. This is on its bottom, this one is also on its bottom. If I take a next thing, you see again you are getting zero phase difference. Why? Because on its top, again top, is the bottom of the wave. Oh my goodness, we are coming up to be same. Now if we compare the phase differences between S1 and S5, if I take this one, you see here's this ray is having it's on its top, the other one is also top, a bit later it is coming. And if I take this bottom, you see the same phase difference is not there. Here the phase difference between them is this ray is a bit ahead of this one, and here it is a bit lagging from this ray 1. That's why the phase difference is there, but that phase difference is continuously not coming out to be constant. So that's where you can that's where you can't say them as coherent sources. Now I know coherent sources. To have the interference pattern, I should have the coherent source. Now let's do an experiment together. See, whenever I explain anything, you just go in your imaginary world. Okay, whatever I say, whatever I am doing here, a thought experiment, try to imagine. Okay, that will give you a really feel for the concept. Now let's do an experiment. Okay, we want to get an interference pattern. So what I did is I brought two sodium light sources from the market. Here they are. So I've got two light sources. Okay. And with these two light sources, I'm trying to get interference pattern on the final screen. They both are of same wavelength. Why? Because they are of sodium lamps. Okay. But the thing is, even after getting two light sources of same wavelength, I'm unable to get an interference pattern on the final screen which I can see. I'm unable to get a stationary interference pattern on the final screen. What is the reason? to have the interference pattern, I need two light sources that I have in here. But why I'm not getting the interference pattern on the final screen? So the thing is that these two sources are not coherent. Yeah, I agree with you that they are having the same wavelength, but the other thing, the other one more condition is that for coherent source is that they should have the same phase or constant phase. But these two light sources are not fulfilling the second condition, that is the same phase or constant phase. If we want to understand why we are not getting the stationary interference pattern on the final screen, we have to see the microscopic view. You see, if in here this light source is having a zillions of atoms, okay, we are getting light from this source, it means that we are giving some electrical energy, and that electrical energy is exciting the electrons of the atom, and those electrons are oscillating up down. Each oscillation will produce a photon. Okay, it will take about to get the photon, it will take about 10 power minus 10 seconds. Okay, and those atoms are completely independent from each other. Okay, and similarly, if this is my S1, so this is my S1, S2, and again from S2 you will be having zillions of independent atoms, though they are producing light, and it will also take around 10 power minus 10 seconds to get it. Okay, the problem is whenever you are getting a light from a source, it's like a pulse. It's not continuous. You are not getting light from this source continuously. You are getting pulses, like one photon will go, again one photon. This is how it is happening. Okay, and in here same thing, they are completely independent. Now if you want to have the interference pattern on the final screen, the condition is that the coherent sources, so they have the same wavelength, that is fine. But the thing is that they are not maintaining a constant phase difference between them. At some instant of time, suppose a light ray got a photon, a single pulse got emitted from here, and this wave is something like this. Okay, and at that same particular instant of time, from here a photon gave you a wave which is having the same phase. They are exactly having the same phase between them. Okay, so these, at that particular moment of time, at that particular instant, you will get the interference pattern on the final screen, no doubt about it. But just after the 10 power minus 8 seconds are gone, you won't be having the interference pattern on the final screen. Why? Because this wave got finished. Now you will be having a other wave, so this might not fulfill the same phase condition. Okay, so this might be coming something like this, and this wave is not having any phase relation with this. You can't get the fixed phase difference between them. The phase difference between the light sources from here, the lights from here, they can't be fixed. They can't have the fixed phase difference. Why? Because they will change with the 10 power minus 10 second of time. They'll be coming completely. Sometimes even if at some particular time the phase difference got matched, but that phase difference won't last for 10 power minus 10 seconds. Again the next photon will come, and that photon might not be having the same phase as this wave is having. So that's why you can't have the stationary interference pattern on the final screen. Okay, so that's the problem. So you can't just have two you can't just get the interference pattern with just two light sources having same wavelength, and the pattern which you are getting on the final screen, you can only see this pattern which is continuously coming going, and if you have a high power camera which can take the shutter times of 10 per minus 10 seconds, with that camera you can see the interference pattern with these light sources. But that interference pattern is not stationary interference pattern. Why? Because in these two sources are not having any fixed phase relation between them. So the problem is that you can't just have an interference pattern with any two light sources. But we want to study light. We want to have the stationary interference pattern so that we can find out so many things about it. We are curious about the light and we want to study. So the thing is, to study light and to get the stationary interference pattern, a scientist called Thomas Young came up with his great idea, and yet the simple idea. His idea is something like this. We did in the double slit experiment. Okay, so we'll be using. He used only a single light source. Let it be S, and we have the two slits. So this simple setup can give you a coherent light source. How come? You see now. So it is a monochromatic light source which is producing light which is having a single wavelength. Now the same light, the light is going from this source and will be coming from this source, and the same light is coming from the second slit. Okay, I messed it up here. So the Young's idea of reducing the coherent source is, we'll take a single light source, a monochromatic light source having single wavelength. So here's the source, and from this source we'll get light from slit 1, and from the same source I'll get light from slit 2 to the slit 2. Because the source of light for slit 1 and source of light for slit 2 is coming from the same source, that's how they'll get the same wavelength. And the other thing is that they will be having a fixed phase difference between them. Why? Because they are just coming from a single source. There are no two sources. If you have the two sources, this thing will undergo. They can't have a fixed phase difference between them. But here, they both are giving light from a single source, and it's a monochromatic source. The other thing is that they always have the fixed phase difference between them because they are coming out from a single source. This was the idea of Young's to produce the interference pattern. And this type of interference pattern which we will get on the final screen is known as interference due to division of wavefronts. Yes, you will be having a wavefront. Okay, so this whole wavefront we are splitting up into two parts. The one part of this wavefront will come out from here, the other part of this wavefront will come out from here. So that's why we call it as interference due to division of wavefront. Okay, the one which Young's double slit experiment, the interference pattern is due to interference due to division of amplitudes. There's one more called interference due to division of division of amplitudes. We'll be studying it later. So that's it for today. Thank you so much. By using the Young's double slit experiment, you can find out